Hello and welcome back to your AP Physics 2 review. Welcome to day 3 of electrostatics. Today we'll be discussing electric charges and electric field and discussing how energy is conserved as charges move through an electric field. As always, we'll begin our day with a quick lesson overview. We'll work through what we'll be teaching today, and then we'll do our daily warm-up where we start with yesterday's review question, do a quick warm-up question, and then move into what you need to know to be successful about questions involving electric field and conservation of energy on the test, which is on May 13th. Then we'll work through some guided practice. Those are questions directly from the College Board. We'll do a debrief and summary as we review what we learned today, and then we'll leave you with an AP exam practice question, and we'll start our day with that question tomorrow. I'm Joe Mancino. I teach at Glastonbury High School in Glastonbury, Connecticut.
And I'm Brendan Eaton. I teach at Reedy High School in Frisco, Texas. And same as the last couple of lessons, we're going to go ahead and show you the rest of the course overview for a review for the AP exam. We are currently right in the middle of electrostatics. And after electrostatics, we'll move into circuits and magnetism. And we really hope that you've taken some time to figure out which of those subjects you want to spend the most amount of time on, and be sure not to miss our practice questions and review videos. And as far as today is concerned, we're going to start off with force and fields, specifically talking about force being an interaction between a field and a charge. And we'll also talk about electric field, force, and charge.
And then as we discuss what the electric field is, we'll talk about the vector nature of a field, how direction matters. We'll talk about the fact that the electric field is another inverse square relationship, and we'll discuss the field caused by a charge distribution, that's several charges arranged in space.
And some topics that you do already know about that we need to tie back in is conservation of energy, specifically electric potential energy, and energy transformations in an electric field.
By the end of this lesson, you'll be able to compare the electric field strength at various points, determine the direction of the electric field from a distribution of charge, and calculate the speed of a charge after it's accelerated by a field.
And we have lots of skills that we will address today. We're going to use representations and models. We're going to be able to justify which math to use. We need to apply that math and explain phenomena, probably with that math, make claims and predictions, and connect concepts across topics.
Yeah, so a light day, not a light day. So here comes the warm-up. The question that we left you with yesterday. You had to draw vectors to represent the forces acting on a little plus Q charge from two other charges. The upper positive charge, that plus Q charge, applies a repulsive force on the plus Q charge, and the bottom charge, that minus Q charge, applies an attractive force because they are, though equal in magnitude, opposite in sign. So you had to draw those two vectors. Then you had to determine the magnitude and direction of the total electric force on the little plus Q charge. F1 and F2 have the same magnitude, so their horizontal components add to 0. I only paid attention to the vertical components here. The magnitude of either of those forces is Coulomb's constant, K, times the big charge times the little charge, divided by the distance between them squared. So the vertical component of either force is that total force times the sine of that angle. So I did a little algebra, and that's great and all. The important thing for you to realize on the AP test that's coming up in May is that you won't be expected to type any algebra or do any derivations like this. You'll instead have to interpret these equations. So you may be given an equation like this and asked to interpret it. So the reason we chose this question is actually for the follow-up, which says that plus Q charge is moved way to the right, very far away. Explain why the magnitude of that force depends on 1 over x cubed at great distances. Well, at great distances, the denominator of that fraction, that x squared plus d squared, that approaches x squared. If x is way bigger than d, that's basically an x squared term. And because of the math that was going on, we had x squared plus d squared times the square root of x squared plus d squared, which is the same as x squared plus d squared to the 1.5 power. So at very large x, that section of the equation is x cubed, because the contribution from d doesn't really matter. All right, and as a warm-up today, we're going to compare electrostatic forces and gravitational forces. So in a hydrogen atom, right, a single dense positive nucleus is orbited by a negative electron. Now, obviously, you can't draw an atom to scale. This is my terrible try at that, and it's not very good. But consider the ratio of the gravitational force between that proton and electron to the electric force between that proton and that electron. Now, College Board could give you all kinds of data, pardon me, regarding the distances and the masses and the charges, and you could calculate that ratio. But I think a more important question is to say, what if instead of a tiny, tiny fraction of a billionth of a meter, we made that separation distance an entire centimeter? What would that do? What would changing that distance do to the ratio? Would it increase the ratio? That is, would it make the gravitational force stronger than the electric force? Would it decrease the ratio? Would it make the electric force weaker more? I said that backwards. Would it make the electric force stronger more than it would make the gravitational force stronger? So which one of those would happen? Would this ratio increase, decrease, or stay the same? Well, let's take a look. The ratio of the gravitational force to the electrostatic force is the ratio of gravity, that's gmm over r squared, divided by kqq over r squared. But gravitational forces and electric forces have that same idea of distance from each object. So the radii just cancel out. Those distances cancel, and we're left with gmm over kqq. And at any distance, that's always the same ratio. So the ratio of the gravitational field strength between two objects divided by their electrostatic attraction or repulsion, that ratio is going to remain constant. Even though one of those may be larger or smaller, the ratio remains the same. Take it away, Mr. Eaton. What do they need to know?
Here's what you need to know. So like we said in the course over our lesson overview, we're going to start with force and field, specifically talking about electric field strength and the fact that it measures force per unit charge. That would be newtons per coulomb. And that force is charge times field. Now, as far as electric field is concerned, the review is going to cover electric field being a vector quantity, and it's represented by a vectored field diagram, which you've probably seen that before. It looks real messy. There's lots of vectors everywhere. The electric field is an inverse square relationship, as Mr. Mancino kind of touched on with forces at least, but we're still talking about that inverse square relationship. We need to calculate the electric field strength around a point charge. You should be able to graph the electric field around that point charge. You should calculate the electric field around a sphere, graph the electric field around a sphere, calculate, graph. There's lots and lots of fields and graphing and calculating and graphing and calculating. Now, as far as conservation of energy is concerned, we will tie that in today towards the end of the lesson, specifically talking about the change in electric potential energy inside of a uniform electric field. And we'll use conservation to analyze the motion in an electric field. When it charges inside of that field, we'll analyze the motion with that. All right, so let's go ahead and jump right into fields. You've heard fields many, many times, but the general definition of a field is just a region of space where an object experiences some sort of force. So as you see on your screen, you have a picture of the Earth, and on the right-hand side, it almost looks like that might be a charged sphere of some sort. It's hopefully not drawn to scale, but on the left-hand side, you know that if you were at the point where you see the dot and there's a vector coming off of it, if you were there, you would experience a gravitational force because you have mass. The Earth is pulling on you. And we won't get into Newton's third law. I mean, you pull on the Earth as well, but you are the object and you experience a gravitational force. Whereas the object on the right-hand side, let's assume it's a charged sphere of some sort. Maybe it's just a really tiny little BB that's charged. If that has a charge and it's inside of an electric field, that means that that charged object experiences a force, an electric force in this case, instead of a gravitational force, like we've seen in the gravitational field before. So gravitational field strength is going to answer the question, when we go back to the Earth and we talk about gravitational field, how much would 1 kilogram of object weigh if I were right here? That question can be answered whether or not the object is actually there. You don't need the object to be present to calculate what the gravitational field strength actually is. Very similar to electric field strength, it answers how many newtons of force would 1 coulomb of charge experience if it was in this exact point in space. And again, that question can be answered whether or not the charge is actually there. It's strictly a concept in knowing the distance away from a charged object and knowing what the strength of that field is. Now, fields also attribute properties to empty space, whether or not matter is actually there. Just like gravitational field is force per kilogram and the electric field is force per coulomb. It could just be empty space and we can calculate what the strength of those fields actually are.
And that's always an interesting topic for my students. I think it's one of the hardest things to grasp about the concept of a field. A field describes a region of space in which there may or may not be matter present. So my calculator, for example, is about 500 grams, give or take, which means it has a weight of about half a Newton. Now I can say, how much does my calculator weigh when it's in my hand? And the answer is obviously half a Newton. But gravitational field describes a different thing. Gravitational field says, how much would a half kilogram object weigh if it were in your hand? And that has the same answer whether or not matter is in my hand or not. Electric field does the same thing. Just like weight answers the question, just like the gravitational field answers a question, how much does this mass weigh? Electric field answers the question, how much force does this charge experience? So just like W equals mg, F equals QE, where Q is charge and E is electric field strength. So if you were to calculate the electric field using this, you would say that electric field is the amount of electric force felt by any particular speck of charge. So because we know how to calculate electric force, KQQ over R squared, we could divide electric force by Q. So here's the equation for electric field directly off the equation sheet. That's the magnitude of the electric field vector is 1 over 4 pi epsilon naught times the absolute value of the charge divided by the distance from that charge squared. Now, very specifically on your left, notice there's a positive charge Q, and we are measuring the field some distance away from that positive charge. In the calculation of electric field, that's what the R term means. It means the distance from that charge of interest. How far are we from the charge? So the pink charge makes the field. And another charge will experience the field and interact with the field. The pink charge makes the field. Now, of course, we never write 1 over 4 pi epsilon naught in AP Physics 2. We write KQ over R squared. So the electric field is KQ over R squared. Now that's the magnitude of the field. kq over r squared. But you'll notice it is a vector. Electric field is a vector. Electric fields point towards negative charge, and electric fields point away from positive charge. But you may recall, positive charges are repelled by other positive charges, and positive charges are attracted by negative charges, which means the electric field vector points in the direction that a positive charge would feel forced. I'll say that again. The electric field points in the direction in which a positive charge would feel force.
It's so important to remember that. So if you have a positive charge, the pink charge on the right-hand side, and you're looking specifically at point P, what direction is the electric field caused by the positive Q charge, the pink charge? So just taking into consideration and note here that there's not actually a charge at point P. We're strictly asking, what is that electric field at point P? So like Mr. Mancino just said, an electric field points in the direction that a positive charge experiences a force from the field. So in this case, no, actually in all these cases, the electric field is going to point away from the positive charge. So since point P is along that x-axis, it's just going to point straight to the left. But let's change it up just a little bit. So which labeled point could the positive Q charge be moved to keep the field at point P in the same direction, still pointing to the left? So imagine moving that charge to position A, position B, C, D, E, and think about what direction that electric field would be pointing at point P. Now, if you remember doing this in class, you know that electric field, on charge Q, the electric field points up, it points left, it points right, it points down, and all angles in between. That field is emanating from this charge, right? So if you put the charge at point A, which way would the electric field point at point P? It would point to the right. So that's not one of my good choices. What about B? I think it would point at an angle. What about C? It would still point to the left. It's pointing away from charge Q. What if you moved it to point E? It still moves or points to the left because it's pointing away from the positive charge. And if you moved it to point D, you would have a weird angle vector coming off of it pointing at point P. So the answer to this is point C and point E. I could move that positive Q charge, the purple pink charge, to C or E, and it would still point to the left. The electric field would still point to the left.
But this is AP Physics too. We're not just going to stick with one representation or two representations. We are going to try to represent physical phenomena every way that we can. So here it is graphically, graphing the field around a point charge. Oh, look, there's the point charge. A point charge, positive point charge of magnitude Q. And at some distance r from that point charge, we say the electric field would be E. Well, electric field, you'll notice, was an inverse square law. That means at twice the distance away, the electric field magnitude would only be 1/4 as much. And at 3 times the distance away, the electric field magnitude would only be 1/9 as much. So we can calculate it, but as a smart AP Physics student, you need to be able to graph the idea that if the field is magnitude E at distance r, it's only 1/4 of E at 2r, 1/9 of E at 3r, and a 1/16 of E at 4 times the distance. Now you may have to identify a good sketch of electric field, and a good sketch of electric field would be one that shows this 1/r² relationship. So again, there's the image showing the calculated electric fields. But what happens when we're measuring from a point even closer than r? What happens if we're measuring the field at less than the radius of the charged object? If we're measuring the field inside that object? Well, as always, we would graph the other points and make a best fit line. But you might notice that at even closer distances, this line asymptotically approaches infinity. It gets really high. But at spaces inside the charged object, that's inside of that pink sphere, whatever it is, there is no electric field. The electric field inside of a charged conductor is 0. And that's the part of the graph that I want to focus on right now, that flat portion right there. The mobile charges on a conducting object, they spread out in a way to make the electric field inside the object 0. Charges push each other away. All those tiny electric charges are repelling from each other, so they spread out as best as they can. The consequence of that, the result of that spreading, is to make the electric field inside that conductor equal to 0. Now, as an AP Physics 2 student, you need to know that for a sphere, that means that charges are spread out uniformly across the entire sphere. There is a uniform surface charge density on a sphere. The electric field is 0 everywhere inside the sphere. But for other shapes that aren't spheres, the same is true. Charges organize themselves in such a way as to zero out the electric field inside the shape. That last word should say shape and not just sphere. So, where in this charge distribution, which of these marked points has the greatest field magnitude and which one has the least field magnitude? Now, before we even go to answer, what you're looking at is called a vector field. You're looking at a charge, that's that plus Q charge, and around that charge are all of those marked points delineated by black dots. And at every black dot, there is a black arrow pointing in the direction of the electric field. And the magnitude of the arrow tells us the magnitude of that electric field. So notice at greater distances, the arrows are shorter. So at which marked point does the electric field have the greatest magnitude? And at which point does it have the least magnitude? Well, electric field was kq over r squared. So r is in the denominator of this one. If r is in the denominator, then small distances from the charge have the greatest electric field magnitude, and large distances from the charge have the least electric field magnitude. The electric field near several charges is the sum of the field caused by those charges. So here are two charges, a negative charge on your left and a positive charge on the right. I don't think that negative charges are particularly blue, but again, that's how my physics teacher drew them. And there we are. So the direction of the electric field caused by a negative charge points toward that negative charge. The direction of the electric field caused by a positive charge points away from that charge. So the electric field at any point is the sum of the fields caused by the other charges. Now, if you'll give me just a moment, I'm going to switch the window here and swap what you can see. And bear with me for just a moment. All right, I believe that everyone can now see a window in which I can put electric charges. So here is a single positive charge. And I can use this yellow dot. This is an electric field sensor. And this dot will point in the direction of the electric field. And the length of the arrow emanating from that dot gives me some idea about the relative magnitude of the field. So you'll notice when the dot is here, the field has very high magnitude and it's directed to the left, away from that positive charge. And as the separation distance increases, the field strength decreases. And it follows that 1 over r squared ratio. If I were to put another, and I'm going to bring it and I'm not going to let it go. So the simulation won't begin the calculation until I release my mouse. I'm going to hover this one there. If I let go of this negative charge, one of a few things might happen. The arrow could change direction. It might point left, up, down, or right. So I want you to think about that. When I release this charge, what will happen to the direction of that arrow? And what will happen to the magnitude of that arrow? This is a negative charge, and I'm bringing it nearby a positive charge. And then I'm measuring the electric field about halfway between them. I'm going to let go in 3, 2, 1, let go. You'll notice that the electric field between those charges is stronger than it was when there was only the positive charge. There it is again, and I'll drop it again. And that's because the field between those charges is the sum of the field caused by either charge. The red charge, the positive charge, at the location of the yellow sensor causes a field to the right. And the blue charge, the negative charge, at the location of the yellow sensor causes a field to the right. But what if instead I were to drop another positive charge here, about the same distance away? And I'm kind of guessing on the distance here. I haven't let go yet. What do you think is going to happen to the direction and the magnitude of that red arrow when there are 2 positive charges nearby? And if I got it just right, yeah, I got it. The field adds up to 0. Either of those charges is creating a field of the same magnitude because the distance is the same. But because electric field is a vector, an arrow to the left and an arrow to the right add up to no arrow at all. Finally, what if I put, and I'm not going to drop it, I'm going to reorganize this just a little bit. I'll put this one up here, and I'm going to put another positive charge right here. I'm not going to let it go yet. What's going to happen to the direction and the magnitude of that arrow when I release this positive charge that my mouse is on right now? It's closer to the sensor than the original positive charge, and you can see the field that's being caused by the original positive charge. Well, will the new one create a field of greater magnitude or weaker magnitude? What will its direction be? I'm going to release it in 3, 2, 1, release. So the direction of the field caused by the new charge is left, and it's a much greater magnitude than the original charge. So now you see that the electric field at that location is a little bit down and very much to the left, adding these as vectors. In AP Physics 2, you often have to discuss the electric field caused by a distribution of charge. Now, there are several different arrangements of charge distributions that you have to be able to interpret. You may want to email your AP Physics instructor and ask if they have any good examples that you can practice with. This arrangement of charge has been on the AP test a few times, and there are a few years that you could look at it for, but oftentimes the College Board asks questions about the electric field strength right in the middle, and for you to explain, if I can get it, yep, to explain why the field strength is what it is and what the field strength is at other points in that distribution of charge. All right, I'm going to switch back to the presentation, and we should be back in the slides. So, as a smart AP Physics 2 student, you need to know some things about different charge distributions. Now, we aren't going to go through all of these, but you should be able to identify the force on any one of these charges in any of those 6 different isolated charge distributions. So ask yourself, how would I calculate the force on that particular charge? Likewise, you should be able to calculate the electric field strength at various points in those charge distributions. And we'll take a look at these distributions tomorrow also and talk about some other properties that you might want to know. All right, I'm going to kick it off to Mr. Eden, and he's going to explain the effect of field on various falling electrically charged objects.
Okay, so we know so far throughout the lesson that electric fields point in the direction that a positive charge experiences a force. Now, in this example, in these scenarios that you're about to see, all 3 of these charges, X, Y, and Z, have mass, so they are experiencing gravitational force, and there's an electric field. So if they are charged, they also experience an electric force as well. So let's go through it real quick. Three identical small spheres are dropped in a uniform electric field that's pointed down to the floor. Sphere X is uncharged, it's neutral. Spheres Y and Z are charged, but we don't know what the charges of Y and Z actually are just yet. Now, sphere Z, when it's dropped, it remains suspended in the field. Spheres X and Y fall downwards, but sphere X takes longer to reach the floor. The idea is we need to figure out what the signs of the charges on spheres Y and Z actually are. So knowing that sphere X is uncharged, what force is the only force that's actually being applied to sphere X? Well, it's just the gravitational force, and which way is it going to point? Well, it points downwards. Now, sphere Z, I'm skipping Y for now. I want to talk about Z really fast. If it remains suspended in the fields, I know I still have a gravitational force pointed downwards. And if it's suspended, that means the net force is 0. So I must have an equal but opposite direction force that's pointed upwards. And that force needs to be caused by the electric field in this case. And since it's pointed upwards, what sign of charge do you think sphere Z actually has? Well, I know that electric field points down, and that's the direction that a positive charge would experience a force. So I bet sphere Z has a negative charge, and it's pointing upwards. The electric force is pointed upwards and balancing out the gravitational force. So going to what you see on your screen, sphere X was in free fall. So it fell in a certain amount of time. If sphere Y were to get there faster, sphere Y had to be positive because it was experiencing more than just the gravitational force, pointing downwards. And sphere Z is pushed upwards by the electric force, so it had to be negative in this case. So why did sphere Y fall faster? It's because it had two forces acting on downwards direction, gravitational force and the electric force. Yeah. I don't know if I touched on that. Okay, so in a uniform electric field, it's easy to calculate how much work is done to move a charge. And this is kind of a concept that you bring in from physics 1 to physics 2, and you've been through most of physics 2 already. You remember that work is force times distance, or force times displacement. But in this case, we're talking about in a uniform electric field. And we're going to calculate how much work is done on a charge inside of that uniform electric field. So what does a
really
uniform
quickly,
electric
the
field
word,
look like?
yep, there it is.
Go ahead.
The
Go
word
ahead.
uniform means that at every point in this electric field, the electric field strength has the same magnitude in the same direction. We'll talk a little bit more about where you would encounter a uniform electric field, but as an AP Physics 2 student, in general, you need to discuss how conservation of energy works in a uniform electric field, one in which the magnitude and direction of the field is the same at all points. So at the bottom of your screen, that's uniform field. All right, Mr. Eden, back to the idea of work. You were saying this.
Yay, force times distance. So we know that. We brought that from physics 1 and dropped it into physics 2, and it's all over the place in physics 2. Now, if I know that a charge is experiencing an electric force, we defined electric force as Q times E earlier, and I can make that substitution pretty easily as being work is equal to QE times the distance that charge inside of the field is moved within the field. So what does that look like? Here's a uniform electric field for you. And this charge, this probably a positive test charge still, is moving against the field, a certain amount of horizontal distance d. And notice that that distance d is parallel to the field. Very similar to what physics 1, we taught in physics 1, that when you push on something and it displaces a certain amount, the force and the displacement are parallel to each other. So that's that fx cosine theta, that kind of thing. So in this case, we still have work is QE times the distance horizontally or parallel to the field that charge was moved up and to the left. So what does work do for you? You know that you can use work to store potential energy, which can then be converted into kinetic energy. And if the charge is allowed to accelerate, that's when you're moving from your potential energy into kinetic energy, because we're thinking about things that are at rest suddenly having, after a period of time, a certain velocity. So if work is equal to the change in kinetic energy, or the change in potential energy, which we'll talk more about that later, we could say that QED is still equal to 1/2 mv squared. So we might know the mass of the object, we might know the charge, the electric field strength, and the distance that that object is, that force is being applied on that object to have work and change kinetic energy. And let's actually see how that moves into a practice problem that we have on the next slide for you.
Now, warning, you are not going to encounter a question like this on the AP Physics 2 exam that you take in May, because it needs one of these. It's got to be pretty fancy to get this kind of work done. It's going to take you a little while, and we don't have that kind of time. So here's the whole question with the answer. There's an electron. We accelerate it. It gets up to this speed, and we use conservation of energy to figure it out. Charge times field times distance is 1/2 mv squared. How fast is it going? So you could solve for the velocity and say the electrons in an old school TV go at about 60 million meters per second. That's quick. This is a totally nearly legitimate AP Physics 2 question. In an old tube TV, a single electron accelerates to a speed of 60 million meters per second in 55 centimeters. How fast would that electron be going if it were accelerated for twice as far? If the distance were doubled, would it be going about the same speed? Would it be going a little bit faster, but not a ton faster? Or would it be going twice as fast? That's a pretty valid question. Doubling the distance. Well, that doubles the QED. It doubles the amount of work that's done. Doubling the work doubles the kinetic energy. So you'd think kinetic energy, it's related to speed. Maybe doubling the kinetic energy doubles the speed, but that's not how kinetic energy works. Kinetic energy has a v squared in it. And doubling v squared is not the same as doubling v. So for this electron accelerating twice as far, it's only going √2 times faster. So we've done it. We have finished learning about electrostatics and introducing conservation of energy. Here's some guided practice for you. Take it away, Mr. Eden.
Okay, so you have a charge and a graph. And Mr. Mancino, I haven't seen this slide before. Would you mind taking this one?
I apologize. So
okay.
Here is a graph of the electric field caused by that particular charge. This is the electric field caused by that point charge, where the beginning of the graph up to that first tick mark is up to the radius of the charge itself. So this is the electric field measured as a function of distance starting in the center of the charge. So how would this graph look different if instead of a charge Q, this conducting sphere had a charge of 2Q? Would the graph look like this, like this, like this, or like this? I'll give you a sec with that one. If there were double the charge, but all other things being equal, what would this graph look like? Well, one of the first things you should think about as an AP Physics 2 student is what's different from graph to graph. The first difference I see is that the electric field is either 0 or non-zero inside that conductor. Well, the electric field is 0 inside of a conductor, so it's definitely not either of those lower graphs. The top right graph, I just copied and pasted the graph from the initial question. So the top left graph shows twice as much electric field, but also falling off as 1/r squared. And it's consistent with the idea that the field inside the conductor is 0. Okay, this time we're only doing 3 questions, although one has 2 parts. The first question is about conservation of energy, and it's about moving in an electric field. The second question is about calculating electric field, and the third question is about drawing electric fields. Take it away.
Okay, so here's your first conservation of electric energy problem. And as you see on the diagram, I'm not even going to read the question yet. Let's just look at the diagram. I see a uniform electric field that's pointed to the right. And there is a blue charge. We don't know what the sign of the charge is until we read the problem. So the electric field has a magnitude of 0.2 newtons per coulomb. When an electron is released from rest in the electric field, what's the speed of that electron after it's moved 0.04 meters? So knowing that Mr. Mancino's blue charges are always negative, I should have known that that's an electron. So we could go into a couple of different ways to solve this, but I think the easiest way to start off is knowing that work is equal to a change in energy. Again, that's a concept that comes in the first 6 weeks or so of Physics 1. So if I start with just saying that simple statement, that's a conservation of energy statement right there. So how do you find the work in an electric field? Well, we discussed earlier that work is force times distance. In this case, it's the electric force times the distance. And what kind of energy is changing? It says, what's the speed of the electron? So clearly we're looking for kinetic energy here. So the work is equal to the kinetic energy after that period of time that the charge was moved, that 0.04 meters. So we know electric force is equal to QE, and I bet you've seen this before. It turns FD turns into QED, which is still equal to 1/2 mv squared. I haven't messed with anything on the right-hand side of my equation yet. So I'm looking to solve for the speed. So if I rearrange my equation for speed, I get V is equal to the square root of 2QED over M. And we can just plug some constants in there because we know the charge of the electron, we know the electric field strength, we know the distance, and we know the mass of an electron. And just for fun, if you want to plug that into your calculator, go for it, but I've already got the answer for you. It's 5.3 times 10 to the 4th meters per second. Pretty quick.
Quite, yeah. Electrons are very fast because they are the lightest pieces of matter. So 3 people sitting at home watching this presentation right now. Mr. Eden, I think they're having an argument. They're discussing the motion of this electron, and those 3 people make the following claims. Dana says the electron is negative, so it will move to the left. Since the field is uniform, the electron will move with constant velocity that's proportional to the field strength. So more strength, more velocity, electrons go left. Claire says the electron will accelerate to the right because particles move in the direction of the electric field. Garrett says, since the electron is negative, it will move left with constant acceleration. With whom do you agree? Now, the reason that this question is here is because this is such a classic piece of a lot of the College Board's qualitative, quantitative translation questions. There's a good chance that you'll see something like this on the test in May, where you have to consider different points of view about a situation and pick out parts of an argument that you agree with, parts that you might disagree with. So of these 3, I'll tell you, one person is more right than the others. So let's go point by point. Dana says the electron is negative. Correct. It will move to the left. Well, also correct. Since the field is uniform, the electron will move with constant velocity proportional to the field strength, and that is the one flaw in Dana's argument. The electron does not move with constant velocity. It experiences constant force, but the result of a constant force is not constant velocity. So let's take a look at what Claire says. Claire says the electron will accelerate to the right because particles move in the direction of the electric field, and Claire is only missing one special word, and that's the word positive. A positive charge would accelerate in the direction of the electric field, but this electron is negative. But Garrett says the electron is negative. It'll move left, correct, with constant acceleration. Now, the electron experiences constant force, and the result of constant force is constant acceleration. Garrett had it right the whole time. Here comes the next question.
All right, so here's another conservation of electric energy problem. You have 2 identical spheres, Q1 and Q2 as shown in the diagram. Q1 and Q2 both have the same magnitude of charge. They're both +3 microcoulombs. And it looks like they're separated by a distance of 3 meters. And all the sides of this little triangle that's drawn on your screen, the sides are equal to 3 meters. Now, point P is at the 3rd vertex, which is up at the top of the triangle. And it tells you that it's 2.6 meters above the midpoint between the spheres. Find the magnitude of the electric field at point P. So rather than immediately jumping into equations and math, I think that there's something that you should do first. And that's kind of been a theme throughout this entire series of lessons. You need to figure out if you can draw something on your diagram to help you determine what that electric field strength would actually be. It's very similar to a free body diagram. I just wanted to draw my electric field at point P. So if you look at Q1 is in the bottom left, so it's a positive charge. The fields point away from positive charges. So at point P, Q1's field is pointing up and to the right. Now, since it's up and to the right, I can also break that into two components. That's something that you should always think about when you're drawing fields or forces. Now, field from Q2 is also going to point up and to the left because it's a positive charge. And if you show the components from Q2, what do you think is going to happen to the horizontal components of those two? We're going to talk about that in just a second. Now, once I've drawn that, I jump into the math and I go, hey, I can find the field at least from one of them and say, oh, electric field is KQ over R squared. I know the charge and I know the constant K and I know the distance away from point P. So each of those charges has a field of 3,000 newtons per coulomb. Now for each of those charges, Q1 and Q2, if you look back at the diagram that we drew at the top, the horizontal components of those fields, since they're the same charge and they have the same fields, the horizontal components pointing outwards like this are going to cancel each other out because they're in opposite directions. So the only thing that's left is the vertical component of Q1 and Q2's field that both point up. Since they're in the same direction, we add them together. So the electric fields, since you have two of them, remember you have two, so that's 2 times 3,000 sine 60. That gives me the vertical component that's pointed upwards, and that gives you roughly 5,200 newtons per coulomb at point P. And here's a final question for you. It's a different arrangement of charges and objects. Figure 1 has 2 positive point charges with magnitude Q at 2 of the corners of an equilateral triangle. Figure 2 has 3 Qs, and see where point P is on figure 2. So which of the following represents, actually, I'm not going to give you choices on this. I'm going to ask you at point P on figure 1, what is the direction of the electric field? And at point P on figure 2, what's the direction of the electric field? Since those are all positive charges, we know the field points away from positive charges. So in figure 1's field is going to point, have you thought about it yet? It's going to point down and to the right. Now for figure 2, we know still that all 3 of those charges Q, the fields are pointing away from those charges. So in some situations, parts of the field cancel out, but I don't care about different points around the triangle. I only care about point P. So what direction is the net field in that case at point P? Well, it's down in this case. But I have one more question for you. Why is the vector on figure 1 drawn longer than figure 2? Well, in this case, the reason why it's drawn longer is because the fields in figure 1 from Q and Q are adding up to make a larger field at point P. Whereas in figure 2, the vector is drawn smaller because the fields from the 2 lower left and right hand charges, those fields are canceling out at point P because they're both pointing inwards, resulting in a net field from the top charge pointing downwards. So you're only experiencing a field from one single charge on figure 2 in this case.
Well, congratulations. We have done it again. We've gone through our practice problems, a quick debrief and summary. Just a couple of key takeaways from today. Electric field measures how much force 1 coulomb of charge would feel at a particular point, even when no matter is present. The net field at a point is the vector sum of the fields created by a charge distribution nearby. And that charge distributes itself evenly, distributes itself on a conductor in such a way as to make the electric field 0 on the inside of that conductor. And so we're going to leave you with an AP exam practice question. You're going to need to take a few screenshots. I tried to make this one as big as possible. This is similar to a question you might encounter in May, the right kind of style. So get your screenshots ready. Here it comes. There is page 1. There is a square distribution of charge, and your job is at first just to draw the electric field. Now, can you calculate the electric field? if you know about electric potential, go right ahead and do the second part. You may not know this yet, and that's fine. Now, can you explain how electric potential energy is related to work, and explain how the potential energy of this system would be different if the charges were rearranged? All right, thank you so much for watching. We hope that you come join us again tomorrow. Remember, you can always look back at the previous videos in this or any other subject for which you have a test coming up in May. Hope you're having a great day, everybody.
See you tomorrow, guys. Thanks again.